hopefully, yeah, okay. Okay. So yeah, thanks for giving me this slot. I hopefully it won't be too boring, or I'll do some good of a job to tell you stuff about Chern Simons theory. It's nothing. It's none of my research, and it's just Standa needed someone for this first slot, and this is just my personal favorite topic, and yeah, I've been like following some of the literature and some interesting applications of Chern Simons theory, and so I just wanted to share some things. Hopefully, some of the people will find it interesting, or maybe not. But yeah, feel free to stop me at any point. Since this is a okay, I'm gonna be writing. Oh yeah, here, right. Screen. Do you see my screen now?
Yes, we do.
Yes.
Okay, cool. Right. Yeah, I just wanna talk about Chern Simons theory and it's some of its features. I don't think I'll have time to cover much, but yeah, maybe if people will be interested, I can talk some other time and make more of a comprehensive treatment of some of the things. But basically, why people should be interested in this topic? Well, you can study it for various reasons. The applications I have in mind are in quantum Hall effect, and I chose this because it's very physical. It's a real world problem, and the nice thing is that some of these features of topological field theory are explicitly apparent in this example or this physical problem. So just to remind people, I guess maybe not everyone's familiar with this famous problem. So maybe I'll spend like 20 minutes on quickly recalling what is quantum Hall effect and fractional quantum Hall effect, and what's the deal, and why would you expect something like Chern Simons theory to emerge in this real world problem? So maybe you very physical thing. You have a two-dimensional conductor. Well, that's not very physical, being two-dimensional. What I mean by that is like very thin slab of conductor, and if you attach it to some wires and start doping in some current, there will be current flowing through the through the conductor, right? There will be electrons going this way, right? If the current goes this way, and the usual stuff about the conductor. But the interesting thing starts happening if you happen to have a magnet around, and you create a magnetic field perpendicular to this plane. So in the Z direction. And what happens then? That's something you also know from classical physics, that these electrons in classical approximation, they do start moving in circular orbits, right? If I have my charged particle in the perpendicular homogeneous magnetic field, those particles start moving in trajectories. So maybe some of them will be closed, some of them can go in bigger trajectories and maybe hit this wall. So what this results in is an interesting thing, that you start actually measuring some voltage on these sides. If I attach this to voltmeter, I see there's some electric field generated, which is no surprise really, right? Because you see that first they were moving this way, now they're affected by the exerted magnetic field, and they start moving to the other side. So you start seeing voltage, non-zero voltage on those other sides. What's interesting, however, is that when this is very classical situation, right? There's there's high densities of electrons. It's not like a something, you know, fancy like super fluid or superconductivity. It's just normal material. And yet you see some quantum interesting phenomena happening when you're measuring the resistance across the slab, and you actually see that normally, classically, you would expect that when I'm increasing this B field, the conductivity would increase linearly. But what happens is really that there's this echelon form of this dependence, that I have these like kind of slabs of constant value, and then it jumps and not this, it's just jumps, right? And they happen to be quantized. So there's some sort of emergent quantization happening in the system, and it's interesting that this is happening at very clean levels, even though the material might have impurities, and you know it's far from being something pure and theoretically relevant. That there's this very clear quantization of those levels of conductance and dependence on the magnitude of B field. So that's an interesting phenomenon, and to people some time to realize what's going on. There's interesting layers on which you can comprehend what's going on, and so the one of the things is that at the level of the Hamiltonian of those electrons in the bulk of this material, you can basically study electrons coupled to this exerted electromagnetic field, and you know, you just construct the model and study that. It's interesting though that when you're only interested in response to that electric field, you can actually pass to the you can integrate out those electric sorry for those messages, that my collaborators speaking in the back. Right. So you can actually write some model. You can write like Hamiltonian with some field phi coupled to a. But you can integrate out this phi and get some low energy effective action, which will describe all the interesting phenomena, and that action you receive will be just dependent on this field A, and it turns out that the resulting action is the Chern Simons theory, and and there's actually quite a few phenomena happening in this model, which can be all accounted for just by studying and quantizing the Chern Simons theory. So these are interesting things. The first thing is that it so happens that a priori you have electrons in your sorry, are there questions? Maybe someone was no, it was just sorry, but yeah, if you have any questions or comments, maybe I'm also saying nonsense because I'm not really a condensed matter physicist or anything. So please feel free to jump in and tell me what is the right thing to say about.
So phi is supposed to model the electron field, or
yes.
So
I can.
You think of it as a scalar, even though.
Yeah. Sorry, this was just schematic. Yeah, I would. Yeah, if I were correct, I should really have that something like this probably. There's also a way to describe it. The first one. Yes.
May I also ask? So, could you please go a little bit up and sorry, you probably told it, but what's on the y-axis of this graph?
There was the conductance.
conductance. Okay. Thanks.
Right. The thing is that so there's two different things. Either when the material, the most prominent lines in this graph will be integrally spaced, and to describe that, you really just need first quantized model of particles moving in the electromagnetic field. You might know the words like Landau levels. That's something, you know, when you couple your quantum mechanical system, when you literally study non-relativistic particle, this thing, and couple it minimally to electromagnetic field, you might recall from quantum mechanics courses that this would be the way to do that, right? And then you can quantize particle in the presence of homogeneous magnetic field. But what I mean by this would be two-dimensional Hamiltonian in the presence of the magnetic field. And you'll learn that there are these infinitely degenerate lines in the spectrum of this Hamiltonian, and they will correspond to somehow to these lines. So you will explain nicely how this phenomenon of integral quantum Hall effect by seeing that there's these bands of infinite degeneracy, and the conductance has to jump because there's gap between among all those lines. However, there's actually something more interesting happening, and that is that there, if you zoom more in, there will be actually some non-integrally spaced plateaus in the graph, and that would be referred to as fractional quantum Hall effect. And for that you need something more interesting, and what's actually happening is this so-called fractionalization. And fractionalization is an interesting phenomenon which happens exactly when you're coupling Chern Simons, or well, it happens in various physical phenomena, but it could be modeled by coupling some quantum field, or even at the classical level, it could be sort of understood. It so happens that every field has this primal statistics associated to it, right? We know that field scalars, we expect that if I put scalar in one point and another scalar field operator in another point, if I undergo monodromy of this guy around the phi, it will either flip a sign or it will remain the same, right? There would be the distinction between bosons and fermions. Know that this is we're in 2D, so there is no other way to intertwine them. It's really just going around, taking one operator around the other, so I can either have bosons or fermions. That's usually what we're taught. But in 2D, and in particular in these special situations with magnetic field present, you can actually see that those particles sort of transmutate and change their statistics. They become dressed particles, and it so happens that they sort of carry some infinitesimal magnetic flux coming with them, and this results in effectively changing the statistics of the particles. They will later on. It's not something we will get to, but it's something what then accounts for this fractionalization of in quantum Hall effect. So what can happen then? That, you know, instead of just permuting two particles, you can permute them and actually obtain some phase here, which is dependent on the okay, depending on the level of Chern Simons. Right, so normally you would have just plus or minus here, right? But this is new phenomenon, and the particles like this are called anyons. So this is something interesting you can see in Chern Simons theory. But okay, anyway, this was just rant about where you can apply and usefully some of the technology developed in Chern Simons theory. Are there any questions or not? If not, then I'm gonna continue with some recap of Chern Simons theory, and we'll kind of look at this flux dressing or flux attachment. So okay, then okay, I'm gonna talk a little bit about Chern Simons theory. So what is Chern Simons theory? I'm going to only talk about. I guess the audience is advanced enough to not be scared of forms, right? So I can write easily this this action, the action for Chern Simons theory. It's something. Note that trivial fact is that this can only be written in 3D, right? Whereas the usual kinetic term for Yang-Mills field that's possible to exist in any dimension. There's this guy that only really lives in 3D. This is one form and two forms. So that's the only way I can put those together to integrate over whole space time. Right. This is abelian version. There could be also non-abelian version, which plays a role in other physical phenomena. That we will the way they would enter would be by an extra term like this, and our trace here because connection is then matrix value one form, right? But nevertheless, for what I want to talk about, I'm just going to restrict myself to U1 gauge field. So this term is not present because they are same connections taking values in just number, right? In say I or R, which is Lie group of U1. So this term is not there, and you have just this free nice little Lagrangian. It could also be argued that in a sense of effective field theory that you can actually because the way Chern Simons appears in a description of quantum Hall effect is via passing to effective field theory of low energy excitations, and what this means in practice is that you identify your fields in question, you identify the right degrees of freedom, and then you write everything you can consistent with the symmetrics, right? So both of these are gauge invariant. Well, Chern Simons is not really gauge invariant. But it's almost gauge invariant up to boundary terms. So you can just make a combination of these guys and maybe something of higher order. But it turns out that in low energies, this is more prominent of a kinetic term than the F star. So yeah, in low energies in 3D, this will dominate, and yeah, it's a nice term to study on its own. However, you would maybe expect if you don't play with Chern Simons theory that they would be pretty much the same as Yang-Mills theory, but which would be wrong. It's actually behaving totally differently than Chern Simons than Yang-Mills theory. The reason being that this action is first order in derivatives, and so just a quick recap in Yang-Mills. You might remember that we had our F mu nu, which consists of E and B's, right? There was this B block, which was spatial part of curvature, and E was in the temporal part of curvature. And then when you were quantizing this theory, it turned out that that you can take your AIs to be like axis, the canonical coordinates, and for them, each of them has this EI being its momentum associated to it. Why I'm writing I here and not mu is for a reason. I'm not just being sloppy about indices. It's really that a priori you have a mu guys, but then you realize that a zero guy is actually a Lagrange multiplier enforcing the one of the constraints of in the theory. Same will be true for Chern Simons. However, it won't be true anymore that the E's will be canonical conjugate momenta to B. Just to maybe just to quickly spell that out, because that's really simple and quite crucial. That if you have a three-dimensional Chern Simons field, x dx ay dy az dz, and then if I it's customary to pick one of them. Sorry. Y, x, and t. I was gonna do the organization. Sorry. So if you feed this into the action and crank up the machine, you see that AT is never seen in the action with the dot over it. So for obvious reasons of antisymmetry it can just never appear like that, right? So if T is on one of these indices, partial can never have T, otherwise it will be zero, right? So it turns out that this just enters as an auxiliary field, as a Lagrange multiplier, and only fields carrying dynamics are X and Y. So what is that really? So after the dust settles, if you just spell out the indices here, it turns out that you get a term like this. You get a sort of conjugate term to it, and then you get this. So how do you interpret that? It's a constraint here saying that if I split my three-dimensional manifold to we're quantizing, right? So we're not really having any three-dimensional Lorentzian manifold, but we have it as a sigma times R, which I denote by a line with this index T. Right, so we have this splitting, and it if the A0 lives here and AX, AY are the connections on sigma, then I see that this Lagrange multiplier, even though it wasn't burned in the covariant form, is enforcing this constraint that that the field on those equal time slices is flat, right? Because this is saying that if I vary with respect to a naught, it says that fxy, which is basically the original curvature restricted to the sigma, and I require it to be flat. So in other words, if I'm going to be quantizing, I don't think I will, because there's probably not time for it now. Yes.
So I guess there is an important minus sign between the two first terms, right?
Oh yeah. Sorry. Yeah.
Because else you could get rid of them by integration by part.
That's true. Yeah. Thank you. Sorry. Yeah. Yes. Silent here. Yes. Thank you. Yeah, but how just a comment on how would you quantize this? You can obviously you can take a long way, but you can also be smart about it. And the long way would be, you know, a canonical analysis. You would look at the canonical momenta and realize there's some constraints, and you would calculate the secondary constraints and apply this whole direct technology. But you can also know the simple thing, and that is that if you stare at this first part, you look at this guy and you identify it as a Lagrange multiplier enforcing a constraint, right? But you can look at this at these two first terms, and you can note that it kind of looks like PQ dot term, right? And even more so, if I integrate this by parts and up to boundary terms, I can just get rid of it on the expense of, you know, having two here. Yeah, whatever. But the thing is that yeah, it really has a form of PQ dot term. So the quantization here is totally different. It's not that I have AIs and EIs and you know, creating promoting these to operators and enforcing, you know, commutation relations for these. It would be really commutation relations between these between these two fields, and that would be my quantization. It's quite important that that there is this constant in front, kappa, that's called the level, and it also enters the quantization of the fields, and it has a crucial impact on what is how the quantization, like what is the quantum theory based on the concrete value of the kappa. It actually leads to this fractionalization in the application of quantum theory. But yeah, but I'll focus on something more concrete and not quantum at all. I'm going to describe how this flux attachment can be perceived from just classical considerations of Chern Simons theory. But yeah, maybe are there any questions? No, I guess I didn't really say much. Okay, so yeah, so it's always a good idea to try to first encounter it with some theory to try to see what is the response to classical current, which should be really thought of as these electric these fermions moving in my slab of the material. So if I study that, I should couple my Chern Simons theory to, I should add a extra term. And what this how this affects the equations of motion is by introducing a source term. So you know, a priori my equation was for motion was that connection is flat. Now I really mean the mu nu, like the entire connection is flat on channel. But for current present, it will affect the right hand side. Obviously, it cannot enter with just, you know, just like this, because there's simply not the right number of indices. But yeah, we have star at our disposal. So if I write this makes sense, and this is indeed the correct equation of motion for Chern Simons. It's interesting to compare this to what we know from Yang-Mills theory, because this is equation of first order and of no derivatives on f, right? Normally, so if f is interpreted as e and b again, now there's just one b and two e's, so ex, ey, y, z. then in the Yang mills, I know that if I put a charge somewhere, I create electromagnetic field, right? Like there's a differential equation telling me how the field is propagating or what is happening with the EMP. Here though, it's purely algebraic in EMP, and that's quite a difference, right? Especially in a situation when I have just static charges in my material. So what happens there? What happens when I have static charges? It turns out that so to understand that, I just take this equation and write it in separately for E and B. So for B, I know that this will be my equation, and for E, I get this. Right. So if I have static charge, this is 0. So what I mean by this is that it's a second part of 3 current, right? The J mu would be rho and J I. So I just want static charges. So that would mean that what does it mean? That my rho is E delta X XA. So if I do this, I see this is 0, so it doesn't create any electric field. And now I notice that there is a localized B field in as a response to these local charges, and that's really the first encounter with the flux attachment. So what happens in Chern Simons theory is totally antipodal to what we know from Yang mills. In Yang mills, I would put in a charge in one point, and it would create full-on field around it, right? Which would be E field being present and B being 0, unless I wiggle my charge. But here it's the opposite. The E is not created, but B happens to be present. But in very strange form. It's just localized in the presence of those right at those points where I put my charged particles. So this is usually represented by saying that I have my electrons here, or some charged particles to the electron, and what happens is that I get this flux, I get this attached B field here for each of these particles, and the strength somehow. So this is called flux attachment. We see that that the field B field is 1/k kappa E, and it's just localized in those points. So by A, I mean the location of the particle. Right. Is that clear? I guess so. Right? That's just classical equations. But yeah, it's nice to write them down sometimes. Nothing hard, but it's nice to, I guess, reflect with Yang mills theory and see that the situation could be totally different. It's also interesting to perhaps study composite Yang mill. That's just a side for people interested. That you can also have Chern Simons with Yang mills theorem or with Maxwell, and that's also interesting. But it's more like Yang mills. The only times you get this weird behavior is when Chern Simons is present on its own. But this is nevertheless also interesting situation, and you actually observe another interesting phenomena you cannot see in higher dimensions, and that is that Yang mills acquires a mass, and that's well, you can give a mass to spin one field, but in a stupid way, right? You can add the a mu term, but that breaks gauge invariance. Whereas if I add the Chern Simons term, I effectively generate mass to these a mus, but it's still gauge invariant, and that's only possible by the interaction with the Chern Simons or interplay with the Chern Simons term. But yeah, that was just a side, just an interesting fact of life. Nevertheless, for Chern Simons, this is happening. I can also calculate AI, the potential, which is important for quantum mechanical considerations, and that if I just solve the right equations, I get this. Okay. Right. Square. So this could be further simplified or rewritten in more clear form, and clear form in a sense that we will see that it's actually almost trivial what this gauge field looks like. This is also, if you think about it, it's a great model for this Aharonov-Bohm effect, because you can just study one particle with this flux attached, which is localized in just at the position of the particle. There's no B field around it, and yet there's a potential, and you can have the analogous situation to what you know from Aharonov-Bohm when studied classically. This is really like a correct response to charged particle and seeing Aharonov-Bohm in field theory. Right. So how you can rewrite this is in this interesting form. Argument x minus x minus. So what I mean by that, word of warning is that it's not pure gauge, because these functions are not not regular. They have branch cuts and singularities. So it's you can swipe swipe the potential under the rack and say, oh, this is vacuous solution. So it's really something, because you can see that these have branch cuts. But it basically tells you that the argument is just a angle with respect to some reference frame origin. So what do you so what I mean by that, just to explain what I mean by this is that if I'm if I put my particle in the origin, I will see that this argument would be a angle between sorry, if I'm measuring my gauge field here, it will be the angle that. So now, interesting observation, which is very topological in nature, is that I know that there's these measuring a field is not really something physical, and I can measure its holonomy, right? That's the gauge invariant information about my gauge field. So what would happen if I try to calculate the holonomy? So holonomy would be the path order exponential, but in Mills, sorry, in U1 Chern Simons, it's just this line integral with possibly some prefactor. So this prefactor might seem a little ad hoc and kind of strange to put in, but maybe it's good to reflect with the non-abelian gauge theory, because to define my my holonomy, I need to prescribe the representation my gauge field is in. And U1s, they also have representations, right? They are just it's a commutative group, and every irreducible representation is one-dimensional, and this M has information about the weight of about which representation I'm in. I need to tell myself how many times I'm. Yeah, it's a weight of the one-dimensional representation. So it's natural to have that extra number there. And now I can calculate this this holonomy, and it actually, it's almost trivial, but not quite. And so what's non-trivial? There's these two different situations to be distinguished. One possibility is when I start here and start integrating my holonomy and come back to the original point. So if when I'm doing that, look at this formula. It will literally count if I integrate that. It will count this increasing and decreasing angle as I go around the loop, right? So it will be decreasing, 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 and then increasing again, and then we'll come back to this to the same point, right? So I'll be tracing it with these rays the whole time, and you can, you know, if you stare at it for a little while, you'll see that after you've done the whole closed loop trajectory, you'll end up having the zero angle around that origin. So if I, in other words, if I take the holonomy around enclosing none of the centers of the classical source, I get zero holonomy. So there's almost nothing happening around the closed curve, which doesn't contain any of the of those charges. Whereas a totally different situation happens, and you probably can expect what will be the result. That if I go around the origin, I go around the origin where my particle is, I will acquire non-trivial holonomy, and then that non-trivial holonomy will be proportional to the charge of the particle sitting in there. So it will be I m e. The m is just a fixed m, then e. Then it will be 2 pi coming from summing up all those angles, and kappa here, right? So so now we see this phase I was alluding to before. I should have really thought of, so holonomies, they are again some effective description of transporting particles around some loops. You can actually write this if you put the work in. You can rewrite this as one-dimensional path integral along a world line of particle, and this m would be representing its charge with respect to the electric charge with respect to the A. So if I'm calculating this holonomy, I'm literally taking particle around particle, and what I'm generating is this non-trivial phase. So you see that in the presence of this Chern Simons field, I'm seeing that my particles have these interesting phases popping up, and yeah, just to maybe to generalize this. Even though this may be now obvious, if I had several particles, I could choose to enclose one or more of the sources, or none, and then if I say I enclosed all three, I could do the usual homotopical trick. I'm gonna first do this, and I'll do this loop, and then I'll do the third and come back. Right, these will be traveled along in opposite directions, so the contribution will cancel out. in here. Right. So the only real contribution would be as if I added up these three guys together, and they will give me all the interesting it will give me these interesting phases multiplied together. So this is really, yeah, this is the classical manifestation of the flux attachment. I start with particles, which could be thought of as fermions. If I'm talking about electrons, I turn on this electric field, Chern Simons field, maybe I should call it electric field. And then I see that if I take these loops of particles around particles, I acquire this non-trivial phase, right? There's an interesting thing to notice that you would think that maybe you would think, maybe not, but that this kappa in front, you would say, oh, that's just a prefactor, right? That must have no meaning in the theory whatsoever, right? That's just something I can hide into my gauge field by redefinition. But notice it appears here, and it also appeared in the quantization. So in quantization, here there was kappa in the denominator, and I will also affect the volume of the phase space. So it enters there, it affects quantization, and it also affects these spaces. And what's interesting, so yeah, I won't get to the quantization, even though that's very interesting. But just to say, these phases are affected in an interesting way. And if the kappa was 1 over integer here, then it would be in numerator instead, right? And if m and e are quantized in in some integral units, the phase will be actually trivial, right? So if kappa was 1 over 6, say, then this phase would be vacant. There will be nothing. Whereas if I have some integral kappa here, it actually creates something non-trivial. But you can notice another interesting thing, that that there are certain there's this non-trivial fact happening, that if I go around once, I'm going to generate this E I M E kappa, but I can go around as many times as I want, right? If this kappa will be integral, I can go as many times to make this object to generate extra kappa here, because I'm just, every time I'm passing around, I will generate the same factor one more time. So I can go kappa times around, provided it's integer. And there's actually some quantization of this kappa, so they're always, or there are always integers. And so then I can actually kill this phase after several times going around. And there's an interesting, there's an interesting fact that those phases actually live in Zn group, right? Because I can go around several times, but if I go around n times, where n will be my kappa, then I get, then it's as if I didn't do any of the revolutions. So there's this interesting phenomenon happening with the particles with the flux attached, if the constants are right, if m, e, and kappa have the right values. Similar thing happens in quantization also, and I don't, I guess I don't have much time, but maybe I'll just say that real quick and in words. But maybe, are there any questions before I go to that? No. Okay.
Ondřej,
yes.
you don't have to end in 5 minutes if you don't want to. You can go a little bit more.
Okay. I might need to anyway because I have some meeting. But
Oh, okay.
but yeah, not in 5 minutes, but maybe in like 6 minutes. No. Yeah. No. Anyway, but yeah. So interesting fact about quantization. Just to give you another flavor of this Zetano phenomenon and connection to kappa. Of course, there's a lot of details, and it could be done, in concrete terms. I could maybe talk about it some other time if people find it interesting, or give some references, because there's a bunch of nice reviews where people do a better job than I do. Yeah, but anyway, the interesting thing happens. So imagine now there's actually possibility to. There's these anyons now. I'm gonna call them anyons, which if I have something of charge E and minus E, I enclose. Imagine what would happen if I enclose two charges like that with different but exactly opposite charge, right? I would get zero holonomy. So they seen far from where I put this pair, it's as if I had trivial particle with trivial holonomy, right? Whereas if I go real close, I can see that they are two distinct particles. So I should really think of them, it's as if I had a vacuum and I created this particle hole pair where I have electric particle and hole with the vacant minus E charge. So I can do that, but and they together create like a trivial holonomy. But I should really think of them like a open string or like a branch cut in my theory. What I mean by that is that I'm cool as long as I'm doing holonomies around both of them. But if I cross the branch cut, I acquire one of the non-trivial phases. But then you can actually ask yourself, this is a thought experiment, but you can make this precise. If you're in, I have my slab. When I'm quantizing in my theory, as I was talking about before, I have sigma times r. If this sigma is of finite size, what I mean by that is that it's not infinitely extended slab, but say something finite and with boundary conditions, which I'm gonna do for simplicity as periodic boundary conditions. Then it's me asking to quantize then I'm effectively working at the torus, right? And then I can create this particle hole pair, and I can pull them away. I can pull and extend this branch cut, and I can go around, come back here, and annihilate them again. And what I've created is this spatially extended branch cut, which is topological, but I'm actually identifying this with a vacuum of the theory, and it's not the same vacuum as as the one without any of these branch cuts, but because in particular how do I know that it's different? Because when I'm on a torus, so when I'm on the torus, every holonomy I take, I'm gonna get zero, right? Back, because it's a vacuum on a flat torus, and particular A should be chosen to be trivial. So if I go over one of these fundamental cycles, I'm gonna get zero, right? But if it happens that I have this extended branch cut, it's as if I chose one of the cycles and I introduce this branch cut around it. I can now see that this is a different vacuum of a theory, because if I calculate holonomy around this cycle, I'm still gonna get 0 because I'm not crossing the branch cut. But if I go around this cycle, nevertheless, so it doesn't matter which place I choose. I always hit the branch once, right? So I'm gonna generate the phase here, and there's no way to avoid it. So so that's actually the way to see that there will be a different vacuum. But obviously now once you're accustomed to this, you can see that I can create these branch cuts around any of the cycles of my bundle. Sorry, of my base space of the stores. Right? Here, or I can put them around this, or I can do some toric knot. Right? I can maybe wind it around in some complicated way. If you know some of the homology theory, you'll see that since these are topological, I can deform them in any way I want. It ends up being classified by how many times I wind around the A cycle and how many times I wind around the B cycle. By A cycle and B cycle, I mean this cycle and this cycle. So it's enough to tell you that I wind around this cycle 3 times and 4 times around this. So if I put it together, I can represent it by some toric knot like this, but it really ends up being the same as if I put the 3 of them here and 2 of them like that. Right, but again, it's interesting that these lines they could be they could appear non-trivial, but they are actually not doing anything. That's for the same reason as these flux attached spaces. What I mean by that is that if this kappa is 1, then if I cross the branch cut, I actually generate no holonomy. So in theories where this is 1, I'm going to have one unique vacuum because there's no possible line I can wind around neither of the cycles. Whereas if the kappa is non-trivial, I can put several of these branch cuts, but again I can only put as many of them until they collide to something trivial. So in other words, you can see after little number theory exercise that for each of the cycles I'm going to have this degeneracy of the vacuum. For each cycle I can put k of them, but not by one more, because then I would kill everything and then I would have trivial holonomy. So that's an interesting observation, and indeed if you study quantization of these anyons in quantum Hall effect with non-trivial statistics, I didn't really get to that, but you'll see that the vacuum of the theory is described by same vacuum degeneracy as the Chern Simons with the level k. So that's an interesting phenomenon, and I guess I mean there's several interesting things one can do now. One can study the theory on a surface of genus G, and some ramification happens. But yeah, I guess if I can just leave you with this, that there's this interesting flux attachment phenomenon and interesting vacuum degeneracy for different for each level, and it actually yields observable physical phenomena, and I guess one can talk about this for several lectures. This is just flavor of what Chern Simons Theory is about. And it's not just really, it's not just boring topological theory. There's a lot of meat to be understood and a lot of subtle features which only like recently are being properly acknowledged and appreciated. So that's that. Thank you. Yeah, I guess I'll end here. And if you have any questions, then please ask. And thank you for listening.
Yeah, thank you, Ondřej, for the talk. It was very nice. So please, anyone, if you have a question or comment or something like that, so just ask.
I guess it was too fast. Oh, sorry.
Yeah, close. Yes.
Raising,
yeah, I cannot find the raise hand button, but yeah. So I guess, Ondřej, how should I think of this Chern Simons coming in? I mean, in you had a very physical starting point in where you. So should I think of the Chern Simons as an effective theory description in this condensed matter system?
Yeah. I would just couple it to. I would start with the electric. With electrons in form of some quantum field, some fermions, coupled to the background, and then I can integrate them out, and I can look at the I can look at the effective action given by that, and it turns out that the right one, it's an effective action approach. So you do construct whatever is admissible to the set of symmetries you have, but it always that's a strength of the EFT, right? That this Chern Simons, it's the most prominent in IR in any situation in 3D. So that's why it describes literally everything in IR in 3D what can happen, and it's all hidden in that seemingly trivial level kappa. Like many things are different when it's integral or not, when it's one or integer, or when it's integral and stuff like that.
So is that when you move to the fractal effect, if it's not just integer but you have
it's little more complicated, that you actually have to attach another Chern Simons field and couple it to that original Chern Simons field, and then you do some other things to it. But yeah, it's basically about exploiting what other values of kappa you can have. The thing is that there's really a quantization a priori. It's very interesting because a priori there's a quantization of kappa. To see that is it's easy by exploiting the gauge invariance of the theory, and you see that it's not really gauge invariant, it's invariant up to boundary terms, and for that reason the kappa a priori should be integral. But you can actually couple to another gauge field, and when you integrate that, effectively you generate something non-integral in front, and that will yield the fractional quantum Hall effect statistics. And so yeah, it's just a little more complicated, but interestingly enough, it could be done in Chern Simons with two fields coupled to each
other. Yeah. Okay. Thanks. And this kappa, when you start with this theory, let's say with some boson or scalar field, and you do you integrate it out, and you get some low energy effective action, which looks like a Chern Simons. And so, do you start with a kappa in your theory before integration, or do you somehow add it after, or where does it?
Oh, that's interesting. Yeah, that's an important question. It does come from integrating out, and it will be exactly like it's virtually the only parameter you have, and it depends on that, on the system in question. So so that comes as a merchant thing.
Okay, yeah, thanks.
Any other questions?
Mhm.
So if not, thank you, Ondřej, once again for a nice talk, and see you next week.
Bye.
Yeah.